Scott, thank you very much for your kind introduction. And it's great, everyone. Thanks a lot for joining this particular event. And I'm very grateful. And also, BGC, a great supporter of our UC Berkeley systems. And please do come to visit Berkeley when you're in the Bay Area. So what I'm going to do is to share my screen. Scott, can you hear me okay?
Yes, I can, Kenichi.
Yeah, great, thanks. So let me share my screen. So this particular presentation is a shorter version of my ranking lecture, but I also changed a little bit so to entertain you because you can go to the ranking lecture YouTube and watch that. It's sort of a you have to endure for 90 plus or 100 minutes to watch it, but then maybe you can have a little bit of a sort of shorter version right now to see whether this really interests you. The title of my talk is Smart Geotechnical Infrastructure, the Value of Distributed Sensing for Geotechnical Engineering. And it's really about performance-based design, construction and maintenance, and perhaps reuse. I just added this slide because Scott mentioned about this book, and I hope Scott likes the latest version. We just published the fourth edition. You may know that in 2005, wow, 20 years ago, we had one book. Late James Mitchell and myself published this 2005, which was the third edition, and we recently published the fourth edition with a new additional author, Catherine O'Sullivan for Imperial College. So if you do have time, please have a look at this new edition. The talk today is really about emerging technology and how we can use this in geotechnical engineering. Obviously, this is something that I wrote in 2023 about what is smart infrastructure for smart cities. And the vertical axis is the expectation, horizontal axis is the time. Let me just make my cursor easier to see. And then obviously they're always at hype and then goes down and then bring it up. Obviously you are working, and I'm sure you're working a lot on AI machine learning. It can be a hype, augmented reality. I see Scott showing the augmented reality. It can be a hype, but then what we want to do is to bring it to the practice. You already see some of the technology being, and I'm sure you've been using this for many practice engineering. LiDAR, drones, digital image sensing, these are things that we have been working on wireless sensor network, and I'm happy to see that it's being used in practice. Something I want to talk a little bit more about distributed fiber optic sensing later on, and I do say that this has taken me 20 years to bring it to here, but hopefully we can bring it to the market, and that's something that I would like to see from you, what you think about this particular technology. Satellite is coming. The digital twin, we always talk about this, but then if you look at the other side of here, I include socio-technical digital twin, and this is something that we're working on, is to bring digital twin with a social scientist coming into it and how the society can be part of this digital twin. And wildfire evacuation is one of the example of that, and we're working on that very heavily at the moment. But I'm sure you're working on a variety of things to bring it to the practice. Movement is something that geotechnical engineers really want to know. So you see that technology involvement in the past 15 years, computer vision, LiDAR, UAV, that gives you a really in the area of precision of sub-millimeter to millimeter, satellite giving you 10 to 20 millimeter, and then I'll give you more about fiber optic sensing, which is sort of a 10 microns to 1 micron in terms of strain. And then we have a WSN, Wireless Sensor Network. And actually, these are the company that spin out from our research group. You can see a variety of sensor system that came out, but it's really about continuous monitoring at difficult to access sites. And as you can see, these are the precision that will really matter in geotechnical engineering. So really the technology have come to the level that we can use it. I know BGC is working on this all the time in terms of distributed in space. So the data is distributed in space in terms of satellite, UAVs, and sensor or advanced metering infrastructure is what we do. This is from my colleague, Professor Zekos, and you can see we go across different scales. For example, this is a technology which is a wireless sensor technology we spun out 20 years ago. And now it has come to a level that you can have a mesh network like what you have in your home with your Wi-Fi mesh network, but it causes really larger scale in terms of hopping for kilometer, and you can coverage a large distance using LoRa technology. And the technology is really about bringing to the low sampling, but then sometimes you need the data very quickly. So it's about distributed in time. So distribute in space, distribute it in time. So, and in many cases, low sampling data rate is good enough. So for example, these are our sort of a system where you have a sort of a battery, something like this. And then if you take hourly reading using a D cell battery in a mesh topology, theoretically, if you get a good battery, it should last for 20 to 25 years. And this is where we spend a lot of time trying to make these devices really low power devices. But sometimes you need to have a very fast sampling rate, like acceleration, noise, and wind. So for example, like the device over here is about using vibration energy and scavenge that to get the energy to send signals, for example. But then sometimes you can have a device that can trigger when necessary. So you see a little bit of shaking, it allows you to trigger. So that's how we save and try to get the data sets. Because if you do take a reading for 25 to 25 seconds with very high frequency, it only going to last for a few days. I want to talk about distributed and undistributed sensors. This is a tunneling machine that you may know very well. And this particular machine collects a data set, 6,000 data sets every inch it moves, or a few centimeter it moves. And then we can start to use this device data sets to look at geological profile and all these things. And some of you may be working already, but you can have a 6,000 data sets. The question is which one is more important to the other? How do you combine these data together? But machine learning allows you to look back and forth and figure out what is the most important one and how do you combine this data set to looking at what is the geological condition, for example? How do you minimize the ground deformation? How do you make sure the building is okay? How do you run the machine autonomously are something that we're working on. And in the ranking lecture, I do show civil cases of this, but I don't have time today. But have a look if you're interested in that particular part. Now, in terms of monitoring, what is the value? And there are two approaches. One is approach one is our traditional way of set a safety margin, managing safety by snapshots. So we always do factor safety or probabilistic. It's based on assumed failure mechanism. So when you look at vertical axis as your daily life, it may be your daily life every day. You have up and downs, perhaps. Maybe infrastructure have up and downs over there, depending on the external loads that we get. Now, what we tend to do is that we tend to look at probabilistic, perhaps, but you have this particular distribution and you make a limit of unacceptable performance from our experience, and we use factor of safety. Sometimes we have accident and can be surprised, but maybe you recalibrate to find another threshold. Sometimes there's an accident and then it was a different mechanism we haven't thought about. So you recalibrate with a different mechanism and do that. And that is approach one, which is what we often do in our engineering practice. However, in the past, it was too expensive to continuously monitor, but maybe not now. And this is what approach two is about, managing safety by everyday work, which is about real-time monitoring. And it really comes from Professor Holnagel, who works on sort of a safety management for hospitals, nuclear power plants, and all these things, trying to say there's the two approaches. One approach one, which is a more classical, but approach two is about monitoring, learning, anticipating what's going to happen and respond quickly. In other words, you keep on monitoring. You may have some sort of a signature of accident starting to happen, but you can stop and therefore you make a proactive management of your infrastructure. So if you know the actual performance, so this is really about monitoring and knowing the actual performance. If you can do that, you learn how to respond quickly if an event begins to unfold. You manage future unknown demand by reducing unknown risk. You may see that this particular one, maybe climate change or something start to happen, and then that's something that we didn't think about during the design stage, but it allows you to adapt. Identify potential improvements in design construction. If you know the actual performance, you say, maybe I should improve the way I do design and construction so you have a more economic infrastructure. And finally, it may lead to circular economy, resource conservation, component reuse, and sustainable design in a sense that end of life, can I reuse my piles because it still is useful for the next generation of building coming up. Now, when we talk about measurements, we talk about Peck's observational method, and it was in his ninth ranking lecture. I'm not sure you read the observational method, and then often, and I haven't, when you read it very carefully, you start to realize Peck's observational method is not about just observational. He has a design philosophy for this, and I'm going to want to go through this a little bit carefully because I think it's a very important concept that we should always accept and understand what the formal observational method is about, or what Peck, Professor Ralph Peck, proposed. So let's look at this particular Andre shear strength with depth, and then you have lots of data. You can do some probabilistic way of looking at it. But what Professor Peck said is that look at the data which is most probable, which I draw as a green line, which is sort of an average line. He also say look at most unfavorable, which is your red line. I'll go back to this a little bit carefully. Of course, in our design practice, we use something a little bit lower than the most probable. It's like a design line over here as a conservatism. Professor Peck doesn't use that yellow line. He says, perform a sufficient site investigation like what we do over here. Assess most probable and most unfavorable conditions, which is green and red. And then establish a design based on most probable on anticipated behavior. So he is saying, use the most probable parameter and then start thinking about your 50-50 and design based on that. Obviously, his interest was deep excavation, so it's about temporary structures, but that's what he said. Do that, and by doing that, you save materials because you have a little bit more proactive design. You do a design based on most probable, and then you select the monitoring parameters and calculate the anticipated values. That is your 50-50 anticipated values. And then calculate values based on that design, calculate the values of most unfavorable condition. What is likely to happen? And then you have a design B, option B, that will allow you to do if your design A starts to go wrong and what kind of things you need to add during construction so you will be safe. And then you monitor and evaluate actual conditions and then modify design to suit actual condition, adopt design B if necessary. So this is the observational method that Professor Peck utilized and proposed. Now, looking at the sort of a parameter, so you may look at the horizontal axis like your drape stiffness, strength, or friction angle. You may have some distribution. It doesn't have to be normal. It can be log normal. But the point is that you do have a distribution. And most probable is something like your 1 in 2. Most unfavorable may be 1 in 1,000, which I think may be the case. If you use that like a structural engineering, they tend to pick in 1 in 20. Geotechnical engineering tend to think a little bit more one standard deviation. We call it cautious characteristic parameters, and that's what we tend to use in design. So this is how you design, and this is probably what you do all the time. But I think I just want you to sort of think about that as a characteristics, but I'm going to call it cautious parameters. So that leads to when you do a monitoring, how do you define your green, a boundary between green and yellow or amber if you're in the UK, and then yellow and the red, and what is the boundary? And you can think a little bit systematic in this way. Obviously, you have a soil ground uncertainty. This is what geotechnical engineers are good at, trying to figure out what is that. Geotechnical engineers think about what is the actional forces uncertainty. Sometimes we need to think very carefully about what is your mechanism and model uncertainty. Maybe you're using a closed form solution, you may be using a sophisticated analysis. There must be an uncertainty of the analysis method that you pick and mechanism that you pick. You all know that construction creates, even after design, the construction creates uncertainty in terms of performance. And all these come together in terms of the performance. And let's say this is the movement of something, of the ground or retaining walls. Then you have this particular distribution, and you must be thinking about this by combining all those together. Obviously, in design, you tend to be conservative in a certain way, and then you have a conservative sort of a threshold. Now it comes movements, and then they have a monitoring. Monitoring will be actual performance. You always need to compare those, and that's what geo-monitoring is about. You always need to look at what is the precision and data error in terms of your sensor. So you need to make sure that you know the error or precision of your data sets, and then you're going to compare where you are. I'm sure you do this red line all the time, but my proposal to you, and I'm sure you may be doing this already, is to you use the cautious parameters for engineering design. However, we can reanalyze the same design using the most probable parameter to find your 50-50 green. So why don't you pick your 50 and pick your 50-50? And by doing that, you can start to say, by having your 50-50, your good 50 is your green, your between your green and the red is your yellow, and beyond that will be your red. And then you may have your emergency trigger depending on in the seriousness. But the point is that by doing that, you can say, are you in the green zone? Are you be better off in your better 50-50? Or are you be on the worst, not good 50-50? Or if it go beyond your red, you have to move very quickly. So today's talk is about demonstrate how engineering emerging distributed sensor and data analytic tool can be contribute to this framework by seeking to understand the actual performance. And I really want you to think about your 50-50. I'm not sure hear the sound. Scott, do you hear the sound or no? Oh,
No, I'm not hearing any
here.
sound.
Is it okay now?
Yep.
Yeah. So I'm talking a little bit about water leaks and water burst and all these things right now. So I just wanted to show you guys some of the real things, and you can see it'll be nice to have a robot doing this particular work, and that's my dream for 20 years from now. But something that we like to see what's going to happen because it's a tough work. I live in Berkeley, the Bay Area, East Bay Area. This is San Francisco's. Our Berkeley campus is where you see over here is a star. We have a Hayward Fault, which is likely to move in the next 20, 30 years in a big way. These are the pipeline leakage rate that we have for the past 30 years. It's everywhere because of the fault and landslide and ground movements. If you include the corrosion, it's everywhere as well. So we do have a very old infrastructure. The old one is from the 1880s. So we have 150 years sort of pipeline still in use. And there's about 1,000 breaks every year. So that is our challenge. And I can't talk about this today, but we do research on AI, machine learning, and all these things. Can we predict when the pipe is going to break? So that we will repair just before it breaks, and therefore there's some good economy onto it. Now, today I will talk about this fiber optic sensing. This is, some of you, and I know the BGC work on this as well, is that you have a standard optical fiber. Optical fiber is a standard that you see you can use for telecommunication. You shoot a light, and then a small light comes back at every point, and that's called backscatter light. I know where the backscatter light came back from because the speed of light is constant. So if you time it, the light coming back earlier is the one that is a signature earlier, closer to the interrogator. But then if it's further away, it takes time to come back, but that time taking back is really, really very quick. So you can get a real-time monitoring of the temperature, strain, and vibration. So using this particular technology, and we've been working on this 20 years, but let's have an example of this. This is a East Bay Mud water pipeline network. Here we go down a little bit south from our campus. And actually this particular site, I'll show you is that, first I will show you the pipeline network that we have on the near the campus. This is our campus. This is the hill, go up to the hill. This is the sort of a top of the hill, and it goes down to the other side on Orinda. And we have a water treatment plant over here, which bring the water through the tunnel to over here. And then every day we bring the water to these tanks at 150-meter elevation to have enough pressure to this what we call pink zone. So if you look at these pipelines, unfortunately, it crosses through the Hayward Fault. So this is one of the sites that we used a fiber optics to monitor. So again, this is the Hayward Fault. So I'm just zooming the location I just see over here. So I'm zooming right over here. And then what you see is this particular part with the Hayward Fault. And then the left side is moving north and south side, right side is moving south, about 4 millimeter or 5 millimeter every year. And then we attach the optical fiber on this pipeline as well as a trench. And these are the cables that we attach. I hope you see the movie, Scott. Is it okay? You see a trench and the pipe?
Yes.
Yeah, and then we see 3 lines where we attach the optical fiber under the tape, and then tape are really to make sure it's straight line and then it's inconsistent. But then we also inject epoxy at intervals to adhere the cables to the pipe. And by having 3 cables, we can see the bending and actual deformation of the pipe. This is the animation of how the strain is developing in the actual direction with time. In the summer, it expands a little bit. In the winter, it shrinks a little bit. But then with time, you see a more localized strain across the Hayward Fault. And then the magnitude is about 100 to 200 microstrain. Small, but you can start to see some distortion of the pipe or elongation of the pipe as the left side is moving up and then the right side moving down to create that 4 millimeter per year movement. Now we have a distributed strain, so that means that I can integrate from one end, assuming it's one fixed end, and integrate the strain in the longitudinal direction to how much stretching you're having on this particular pipe. And this is what you see. So this is the fixed end. I just integrating that strain to make a displacement profile. During the winter, it sort of shrinks due to the thermal contraction. During the summer, it starts to come to the summer. It goes up a little bit and expansion, but you start to see more exaggerated displacement profile on the fault zone, which is your 4 millimeter. The error of this measurement, the measurement precision is about 40 microstrain, and we develop a cross-run solution of how that error propagates. And you may not see it very clearly, but the shading that you see a shading smaller over here, but more shading on the right, because as you integrate, the error propagates further to the right. But you can see the error is really, really small. So in a sense that this particular movement, we believe it's real. So if you extract that particular one, remove that seasonal effect, and then looking at the movement by the fault movement only, this is what you see in terms of displacement profile from the west side to the east side, and you do see a 4 millimeter movement. And we do have a record from the satellite movement for 20 years or 10 years movement, and then you average the movement for the past 10 years or so and do a statistical analysis, you do see that it's moving about 4 millimeter per year but then this is 1 year data. This is the statistical average of many, many years through the satellite. But you can start to see the different scale that you can monitor using this technology. Now, we also have a cable on two sides, so that gives us the bending strain. And once you have a bending strain, you can integrate twice to get the lateral displacement. And this is the sort of a snaking of the pipe and with time. And it really bothered me when I saw the data, and I keep on asking the students, this should not be right. The reason why is that you see a movement of zero point 0.1 meter, which is 10 centimeters or so movement, snaking back and forth. And then these are the errors. So it's not the instrumentation error that's giving you, because we theoretically we calculate the error because we're integrating for two ends, and then having that integration point, you have more error in the middle, but you do see this particular interesting movement snaking. And then it really bothered me a lot. And then when I look at the trench, and then when we talked at the students and the research and contractors, how they've backfilled, you can see it's difficult to compact the two sides. So what I realized is that perhaps that temperature in the pipe, which is shown over here, can be different from the ground temperature every day, because every day you bring some water from the reservoir, and then they may cool or become hot, depending. So the pipe in the temperature in the pipe may be different from outside. So this is something that you see is the temperature of the water inside, and then you see up and down. And obviously that will give you interesting behavior because of the curvature of the pipe. When the thermal expansion happens, it just do snaking. So if I have no lateral resistance, that means that no soil lateral spring and no axial resistance, which is not probably the case, but no axial spring, and then apply a thermal expansion of the pipe, it does move 10 centimeter or 100 mil. Obviously, you have actual resistance because the pipe is sitting on the soil, so actual resistance may be larger, and therefore, but you do see a movement of some lateral movement. So we start to see some interesting mechanism that we don't think in real, but it's really interesting. So we have a California Energy Commission to showcase how this distributed strain can be used in practice. So obviously LiDAR give you a distributed ground movements. Fiber optic can give you distributed strain, but you do your initial study through the lab and you design, but then can we update? And then update the parameter and then really confirm your mechanism that you assume in your design is correct. And if you do that, you will learn how your pipe is behaving, and then you can make a better action to replace. So for example, in that plastic pipe that you saw, HDPE pipe that you saw previously on in the Hayward Fault, pipe is designed to withstand the movement of, say, certain 70 feet or something like that, but 7 feet. So 7 feet, but then the point is that if it moves after an earthquake, you can start to say, what is the residual life of this particular pipeline? So it gives you idea when to replace. Here's another case of the pipeline for the PG&E. So you see 3 lines. So the point is that once a pipeline is buried, we're not going to see it for the next 100 years. Why not embed intelligence during construction for future generations? We're using that for fiber optics for pavement. So you can see a pavement with the fiber embedded, and then you see a sort of a dog running and become a touch screen. And then we're working with the car manufacturing companies and Caltrans and the others to see, can we make a road safer by having a smarter infrastructure? So here is like a people moving, and this is a water flow for the distributed acoustic sensing, and we do the real-time sort of a mapping of how people are moving and that sort of thing. So maybe in the future I can see, oh, Scott walks in this way, so I can see, wow, this is Scott, because Scott may work in a certain way. You can do geophysics that we're very familiar with, so that's something that we do, especially to find out the water table for liquefaction analysis. Fiber is already in the embedment, so we use a dark fiber for 20 kilometers or so from Richmond to Oakland, and we monitor one of the roads, what's going on that particular road using a distributed acoustic sensing where fiber is already embedded in the ground for communication, and we borrow one of the lands to do that. We do something for the offshore, so we have a cable that is listening, and this is the project where we have a whale singing and using our cable as a microphone to listen, and maybe you can hear the sound of our whale singing in Monterey Bay. And our researchers love this particular project because it's a fun project. Here's another one near our campus. We bury a pipeline and then we have a cable and we really want to look at the leakage. So here we have a sort of a cable that is being attached and then buried. And after that, we start to create a fictitious leakage, start to have a small leakage. I'm going to be quiet. Maybe you can hear the sound. And now we have a big one like this. Now it's obvious, but then what we really want to do is to figure out how this cable can be used. You can look at the frequency of the cable with time and start to see the pipe leakage sound is about 80 to 120 hertz. And we are looking at different cable types in the trench or the pipe. But at the same time, when the leak happens, pipeline vibrates. So you can see the pipeline wall vibration in the 1 to 10 hertz. And you can filter it if you want to look at pipeline leak sound. Scott, how am I doing? Should we stop, or I have one more case study that I can go for 5 minutes or so, and then maybe we can finish off?
I think that's okay. If one of my colleagues wants to correct me, please do so. But I think it's okay, Kenichi.
Okay. I just wanted to give you one example. This is not in ranking lecture, but it's a pile shaft where we put the fiber optics to measure. And this is the CPT data looking at silty clay, sand, and dense sand, and silty clay to look at. Actually, it was a post-grouted shaft test, but I just want to show you when, after this is done, when you apply a load, what is the strain distribution within the pile. So here's a pile with a strain gauges, typical vibrating wire strain gauge. We have a fiber optic to measure the temperature during the curing, which I can't show you today, but strain cables. So if you apply a load, strain will be the largest at the top and decreases with as you go down. And this is the typical load displacement curves. We had 4 piles, so these are the typical load displacement curve. Now, this is the strain gauge data that we have at the level of the loading of 1700 kips. And then you have this strain gauge data that you see over here. Now, you look at this data and say, what is that particular data? And you may say, I don't like this data, so I'm going to throw this data away. However, when you look at your fiber optics data, actually this particular data is true. The purple line is one side of the pipe, and then the red line is the other side of the pipe. In other words, the difference is the bending of the pile. This is the bending in this direction, but it's quite interesting. It's bending in one direction, but then as you go deeper, it bends in the other direction. So in other words, this particular data is correct. It just, our assumption of vertically loaded pile will never bend. If you take an average of everything, it looks nice, and therefore you get a nice distribution of the strain with the gradient is related to your shaft friction and the end bearing is related to your bottom of strain. This is for loading, increasing the load. So this is the same pile as you increase the load. All the data sets that you see in vibrating wire strain looks good if you look at actual data set with a distributed strain. So this data set that we didn't like may be real. We had 4 piles, so these are the other 3 piles. Even though we try our best to vertically load it, because of the small eccentricity, also pile is not properly vertically downwards, there's a little bit of inclination that leads to this kind of bending performance. You can integrate your data sets, and if you just assume there's a fixed two bottoms, then you can see how much is bending, and you can see that it's only a very small movement of few millimeter, it's bending, but you can see, and that's the signature of the strain gauge that you see from the data sets. In other words, your pile is not vertically drilled, so you can see the pile tip, which is shown in the red, and then the top head. So there's always an eccentricity, and that creates the bending of your pile. So the question is that are important aspects of your shaft friction that you want to understand. So you can do a very simple FE analysis with typically you do a TZ relationship with the end bearing, but I'm just adding additional lateral spring. And what we're trying to do is to calibrate our TZ and then PY relationship with our data sets that we have. So back estimation of TZ relationship. This is what we found. So this is a shaft friction with a displacement. And then one is assuming there's an eccentric load that we have a lateral spring. And then the other one assumes no eccentricity, that we don't optimize the lateral spring as well. And then if you look very carefully, let's look at the bottom one. These are the bottom two, and these are the top four. You see that the eccentricity and then non-eccentricity doesn't really have much effect in terms of TZ relationship. However, this is the TZ relationship that we get from our data sets. The error bar is shown in the shaded zone. If you go to the top, a little bit more loading, you do see a difference in terms of effect of eccentricity in the derivation of your TZ relationship. However, when you only look at, because we have lots of data, you can get a small error bar. If you do the same thing for only the vibrating wire strain gauge, we only had few data sets, and then trying to derive your TZ relationship, you have much larger error bar, and then you get your TZ relationship just from the vibrator and strain gauge to optimize your TZ relationship, but the error bar is going to be large. So the importance of what I want to say is that more data you have a better appreciation of your TZ relationship. Now, the eccentricity was an important part of this particular derivation of TZ in this particular case. The answer is no in this particular case. The Tmax is your maximum shaft friction at the end over here. And if we compare the two with the eccentricity and without eccentricity, they're very similar. In other words, without the eccentricity in this particular case was not an issue in terms of bending, was not in terms of deriving your TZ relationship. So I just want you to come back to this one. Hopefully by looking at the data, more data you have, you'll start to understand the real behavior. And I want you to start thinking about your 50-50. You can do that for your pile shafts. You can start to drive your green, yellow, red, maybe just for the low displacement curve if you don't have a fiber optics. But if you have a fiber optics, you can do for every point along your fiber as well as your bottom to start looking at, is it your 50-50 in green, yellow, or red? You can do that for retaining walls. You can start to predict where it's going, and you can start adding your stuff and your support, and then you can keep on going. And then if you start to see you're always green, maybe you in that case say, maybe I don't need to have this final prop. And then without the final prop, I can excavate and save time and save money. And that is another way of looking at observational method, which is not the PEX observational method, but it's a new generation of observational method with the more conservative design, but you have more proactive construction process. And this is discussed muchly in the ISNZG TC. There's a technical committee on this one, and maybe you can join this one if you're interested in as well. So just to come back to, if your analysis is always in red, that you're not good. But if your analysis is always green and your measurement is always green, it means that you're over designing and maybe you need to think about how you're going to design. So in summary, I think there's a lot of interest in the sensor and data analytics. I just gave you an example of fiber optics. By having upon fiber optics, you can use it for quality control, maintenance, resilience against hazards, and reuse. But by understanding the actual performance of your geotechnical infrastructure, then you can be more proactive in looking after your infrastructure. And that is what I call new generation of the observational method. Sorry, I went for a very, very long time, but I just want you to remember that maybe you can try your 50-50. You don't need to tell your client about your 50-50, but just talk with your friends, your colleagues, and test your 50-50 every time you do your design. Thank you very much.
Thank you, Kenichi. And we don't have a lot of time left. I do really want to say that was a spectacular presentation. I'm always thinking of something. I have a list of many, many questions I'd like to ask you.
Sorry.
But they can be for another day. I do, we do a lot of work at BGC with the fiber optics, of course, and yet when I see some of the work you present, I continue to think we're just touching the surface. Maybe one simple question for you, and just because it's your last example, really, there is this practice of thermal integrity profiling
Yes.
of shafts where temperature is used to give some indication of the diameter of the cylinder that you think you've put in the ground. Have you tried combining your work with that? Because maybe that's a short-lived technology.
Yes.
And it's
Actually,
time to move
that
on.
is probably the easiest way to start the fiber optics, and most of our work is about thermal integrity testing. And then I did discuss this in my ranking lecture, so if you can look at it. But the point is that once you measure the temperature, you can also measure the strain. And what we see is some nice relationship, potential relationship with the diameter of the piles changing and actual strain development during the loading. So now you start to link your pile geometry to the actual performance of your pile, which you can start to say how I can do a better design.
Yeah, that's wonderful.
Yeah,
And
yeah.
that
So
leads
that
to the
is
sort of final thought is that when you know more, you have to be ready to act on what you know, right? And if you know so little, 2 points always make a straight line. But if you know a lot, it's harder to understand. So anyhow,
yeah.
it's fascinating. I really appreciate your time and the content here. Yeah, thank you for joining us.
Yeah, thanks a lot. And if you have any questions, just email me and I'll try my best to answer. But I'm very sorry it took longer time than I thought.
No,
I
no,
appreciate it very much.
we appreciate it as well. So thank you. Lauren, I think I'll turn it back over to you now.